Okay, welcome back to my channel, and we're going to be solving an electricity question today. So let's make a start. So this question, like I said, is about electricity. It's one of the harder questions, as you can probably tell from the introduction. And so let's have a look and see what we've got. Okay, so a student's putting a coin into a vending machine that sells food. The vending machine is connected to the mains electricity supply. What is the frequency and the potential difference of the main supply in the UK? Well, hopefully you already know this, but it's 50 hertz and 230 volts. And they're sort of values that you probably should know from your lessons. If not, you kind of need to sort of find a way of memorizing them. However, they should have been explained to you in lessons when it came to electricity in the home. So hopefully you kind of know the answer to that one already. The vending machine identifies the value of the coin by measuring the resistance. So these old vending machines, that's essentially what they do, because each different coin has a slightly different resistance. They identify the coin. So when you put a 10p in, it knows the resistance that 10p should have, and it recognizes the 10p. So let's have a look at the next one. So the vending machine identifies the value of the coin by measuring the resistance. The power dissipated by the coin is 340 milliwatts. Straight away, we can see that this is a unit conversion. As mentioned in previous videos, we need to watch out for these because students can lose so many marks on just converting units. I like to put them in index form. So if you know the prefixes, milli is 10 to the minus 3. And so we don't need to mess around with adding zeros. We can just go 340 times 10 to the minus 3 watts. So that's the unit done. It says when the current in the coin, the power dissipated by the coin is 340 milliwatts. When the current is 0.75 amps, calculate the resistance of the coin. And as I've shown you in a previous video, I like to write the letters over the words because you guys are essentially reading off of a data sheet, which is going to make it easier for us to find the equation we need. So P, I, and R. So if you guys look on the data sheet, this is going to be P equals I squared R. We're trying to find the resistance of the coin, so we can do some substitution. Like I said, it's up to you how you guys do this. You can either put the numbers in first, or you can rearrange to make R the subject. You'll probably make less mistakes if you put the numbers in first, but if you're pretty confident with maths, you can just rearrange it straight away. So P over I squared equals to the resistance, and then we just substitute numbers in. So let's clear this on the calculator. We're going to go for P, 340 times 10 to the power of minus 3 over the current squared, which is 0.75. And that's 0.6. Doesn't say anything about significant figures, so I'm going to just leave it as 0.6 ohms, and that should get us 4 marks. 4 marks for that question, and it's not really too bad. Okay, the next one says coins that are dirty are not recognized by the vending machine. Suggest one reason why. Well, we've kind of already answered that question. It's almost told us the answer up here. The vending machine identifies the values of the coins by measuring the resistance. Well, I suppose if the coin is dirty, that's going to change the expected resistance of the coin. And so the machine won't be able to identify which coin it is. So I think we could probably write something like the dirt changes the expected resistance of the coin. And it's not asking for any explanation, so no need to over-explain on this one. It just says suggest one reason why. And I think that's probably enough to get that mark. And then in the second part of the question, figure 2 shows a different part of sorry, the figure 2 shows a part of a different circuit that is used to monitor the temperature inside the vending machine. Okay, so we're using a thermistor. And they've left out the symbol for a thermistor because I think that's this question here. So this circuit, you've got a 400 ohm resistor in series with a thermistor. You've got a voltmeter around the thermistor, and we've also got a 12-volt battery as part of the circuit. So I'm just going to add the current. It's going that way from positive to negative. The circuit symbol for the thermistor has not been included. Draw the circuit symbol. So this is the resistor with a hockey stick through the middle of it. It's usually what I say to the students at school. So it's just a resistor because it's a special type of resistor, and you put a little hockey stick through it like that, and that's the circuit symbol. So that's all good. And then the next question, I think, is the harder one out of the questions on this. The harder part of the question is this one. And so we've got this circuit. We've got two resistors in series, but one of them's variable by temperature. The other one's fixed at 400. So that's going to be important to this question. It says figure 3 shows how the resistance of the thermistor varies with temperature. Okay, so we know that the thermistor changes its resistance as the temperature changes. It says the cooling system inside the vending machine turns on when the temperature of the thermistor is above 20 degrees. Determine the potential difference across the thermistor. I'm going to highlight that. Determine the potential difference across the thermistor when the temperature is 20 degrees. Okay, well, clearly this graph is part of this question because we can get the resistance of the thermistor at 20 degrees. So the resistance of the thermistor, so I'll just put R therm maybe, equals to 80 ohms at 20 degrees C. Okay, so what does that mean for the circuit? Well, let's go back up. So now the thermistor has a resistance of 20 ohms. No, it doesn't. It's 80 ohms at a temperature of 20 degrees. So if you guys remember the equation you need that's not on the data sheet for the total resistance of the circuit, it's in series, or the two resistors are in series. So we just need to go R1 plus the resistance of the thermistor. You just sum up the resistances. So, okay. And that gives us a value of, well, I don't need to write these values down for you because we've written them here. So it's 400 plus 80. So the total resistance in the circuit is 480 ohms. Now, for any of you who do electronics, or any of you in, the higher sets or whatever, you may already know that the voltage is going to just be shared out in the same ratio as the resistance. And so you guys might be able to work out from here that the thermistor has 2 volts dropped across it. And the, if there was a voltmeter around here as well, this would have 10 volts dropped across it. But that's difficult to see because it's ratios and students don't like ratios. So the best way to do it is probably to stick to the knowledge of electricity that you've learned in lessons. So now what we do is we use V equals IR. This is using the total voltage, which is 12. Total resistance. And so 12 equals to the current times 480. Obviously making I the subject of that equation. 12 over 480 equals to I. So we can get the current in the circuit. So if we clear this, sorry, 12 over 480 is 0.025. So the current I equals 0.025 amps. And like I said, this is why you can split it down into ratios, because now we know that the current in the circuit is 0.025, and it's just a series circuit. So the current in this series circuit doesn't change. So that means that both resistors have that much current passing through them. We can use V equals IR again on each individual resistor to find the voltage dropped across each one. And so what do I mean by that? Well, if we now do the voltage of the thermistor equals to the current times the resistance of the thermistor, we can now work out the voltage. And so that's just going to be equal to 0.025 multiplied by 80. And if we put that in, we get a value of 2. And so you can see there are 2 volts dropped across the thermistor. And so then using Kirchhoff's rule for voltage, the voltage dropped across the components has to be equal to the voltage dropped across the the voltage dropped across the components has to be equal to the voltage given by the battery. And so then we know that because we've just calculated the thermistor as 2, the fixed resistor would have 10 volts dropped across it. And that's that. So thank you for watching, and I'll be back with the next one.